All right, I have some ideas to communicate here about many worlds in emergence and supervenience. It's a synthesis of some ideas that I've come across. I have a tendency to let the perfect be the enemy of the barely adequate. So this time I'm just going to go ahead with the barely adequate. So many people think of many worlds in terms of the image on the left when they hear the term. That's not how I'd like you to think about it for this. Instead, I'd like you to think about it in terms of the image on the right. The image on the right is actually from Wikipedia, and it's a string theoretical brain, like a membrane. But what it sort of pictures is a multidimensional manifold. And it's kind of weird to think about base reality being like this, but physics has taught us, if nothing else, that base reality is probably much stranger than we can imagine. So just go with me on that one. What is many worlds theory? Okay, so it's an interpretation of quantum mechanics, and it has to do with the probabilities that we observe when trying to calculate where a particle is going to end up in an experiment, for example. So you can't predict it with accuracy. There's always some sort of, I mean, the accurate predictions are in terms of probabilities. But once you predict those probabilities, the particle could pretty much end up wherever in actuality. And the worlds are distinguished by quantum events and properties. So, for example, if you have like a piece of uranium and a neutron pops out of that, when that's going to happen is a probabilistic matter. And so there will be some worlds in which that happens at time t, and some worlds in which that happens at time t plus one and time t plus two, et cetera, et cetera. And the reason that worlds are thought of in this way has to do with experiment, because when we actually perform experiments, and by we I do not mean me, I am not a experimental physicist, but when we perform experiments, we do see determinate outcomes. For example, an electron has hit a photographic plate at this location. Um, but we do notice that there is some probability involved in that because the electron could hit the photographic plate in any number of places and seems to do so based upon some sort of a wave dynamic. So for an experimentalist looking at quantum many worlds interpretation of quantum mechanics, one natural way to think about it would be that for each probabilistic quantum event, there are worlds for each possible outcome. So some people think about this in terms of branching, and we'll get to that in the next slide. Um, but really, the Everettian idea, named after Hugh Everett, whose PhD thesis was on the many worlds interpretation, is just to take out the rules of quantum mechanics that dictate what happens when sort of the wave function collapses, what happens when this probabilistic state turns into a determinate state. So many worlds just removes those rules and just goes with the basic mathematical description of the quantum mechanical realm. And so, in that realm, all worlds exist in a single high dimensional manifold specified by the wave function, the Schrodinger equation. So, the only sense in which there is a multiplicity of worlds is from our inability to observe more than one outcome in an experiment. Um, it's still useful to think in terms of worlds because those indicate what we can observe in experiments, but the idea is not that base reality necessarily has a multiplicity of disconnected things, but rather that there is a single, incredibly complex, perhaps infinite dimensionally complex wave function for the entire universe. And that what we see is just some slice of that wave function, and that would be a world. So this image on the left is the famous Schrodinger's cat experiment expressed in terms of many worlds. Here we see a kind of branching where at one point let's say uranium fires off a neutron, which hits a detector, which then smashes a vial of poison. So in the world where that neutron popped out at time t, the cat dies. In the world where the neutron does not pop out at time t, the cat stays alive. And so you sort of see this film strip branching here. We also see diagrams like on the right where instead of time going from left to right, time can go from like down um, uh, to up, for example. And one of the common interpretations of the many worlds theory, or the interpretation, is that we get a branching type structure. So every time there is a possibility of a subatomic event occurring, or a subatomic event happening in one way rather than the other, like the polarization of light being vertical versus horizontal, you get this branching of worlds in theory, where everything else is exactly the same. All subatomic properties are exactly the same except for one difference. And of course, you can imagine how quickly this branching can start to proliferate. Another way to think about it in terms of, instead of branching, is in terms of overlapping. So it could just be the fact that instead of the world splitting, it's just back in time. It is the worlds overlap, and forward in time, they diverge a little bit. I prefer this particular metaphor just because I think it's a little bit more useful, but we have to realize that these are indeed visual metaphors. Now, the macroscopic world, there's a real problem about the many worlds interpretation in terms of how to go from this high dimensional state space of the universal wave function to the world that we observe on a regular basis. Well, one interesting thing is that the macroscopic state of our world, say the world of rocks, trees, houses, humans, that kind of stuff, or the world of events like riding a bike, these can be self-identical over some range of microscopic states. Just to get sort of an intuitive understanding of that, imagine that you're riding a bike, and one of the photons that happens to hit you at the time is polarized in the vertical orientation, and instead of the horizontal polarization. So that riding a bike event isn't changed at all in terms of its macro scale properties by that single photon having a vertical polarization versus a horizontal polarization. Um, so the riding a bike state can remain self-identical, can remain the same state over some range of microscopic states. Now you can imagine that this range of microscopic states would be fairly large, because there are all sorts of quantum subatomic fluctuations that can happen and leave still that macroscopic state the same. Now it's not infinite, of course, because there is some uh, threshold of microscopic changes that would make a macroscopic change. However, the macroscopic state is very robust in the face of potential differences in the microscopic state. Okay, so here I just say the state of riding a bike is compatible with some number of microstates, right? Now, interestingly, this um, this formulation is the same formulation, or is compatible with the formulation of something called supervenience. And supervenience is just the relation where if you have something that supervenes on another thing, so P supervenes on Q, there's no P change without a Q change, but not necessarily vice versa. There can be a Q change without a P change. So let's say P is riding the bike and Q is the polarization of a particular photon. Um, if the state of riding a bike changes, then the microphysical properties of that state will also change. It needs to, right? Because if I move my arm, all of the atoms in my arm and all of the electrons and quarks that make up those atoms, they are also changing position radically from the scale of an atom just by me moving my arm. So any arm change requires some sort of a atomic change, right? But there are lots of atomic changes that could happen and make no difference to my arm change. So that is supervenience. So there's no P change, no macroscopic change without a microscopic change, but there can be many microscopic changes without a macroscopic change. So there are some changes at the microscopic level that would change the macroscopic level. The point here is just that there is a large set of microscopic states that are compatible with a given macroscopic state. So that's supervenience. Now, supervenience characterizes at least epistemic emergence. So, what is emergence? We think of emergence as like, water being wet. Why is water wet? Well, we can look at the microphysical properties and come up with all sorts of explanations as to why water behaves in the way it does, but its wetness itself is considered an emergent property, right? You can't find wetness in the atoms. There are no wet atoms. Um, so that's an example of emergence, and is actually quite a mystery why we even have emergence in this universe. You could imagine a universe that had no emergent properties whatsoever, that the energy released at the Big Bang, for example, just continued somewhat randomly, and no emergent patterns ever existed. So that's a bit of a mystery. And I think it's at the heart of the mystery of consciousness and other mysteries in the sciences as well. And what is epistemic emergence? Well, epistemic emergence is just this idea that when things, when larger scale patterns emerge out of microscale patterns, um, that the reason we can't necessarily predict the macro scale pattern from the micro scale pattern is because of the chaotic nature of the microscale pattern, making it practically impossible for a human being to figure out what those larger scale patterns are going to be. There's an old idea about Laplace's demon, the idea that, or I think Dennett used a super intelligent Martian, the idea that if you can, Daniel Dennett, who I'll introduce on the next slide, a super intelligent Martian where if you could give them the microphysical description in completeness and they're like a super calculator, you could figure out if somebody's going to walk through the door with a bottle of wine based upon all of the positions and momenta of all the atoms in the universe, for example. So the only reason that the Martian can figure that out is just because they have this like infinite capacity for calculation and this infinite capacity for knowledge about where all the particles are and everything. And the reason we can't figure it out is just because we're not smart enough. So this is the idea of epistemic emergence, that in principle you could figure out from the microscale properties what the macroscale properties would be. So there is strong emergence, which goes beyond epistemic emergence, but I'm not going to be concerned with that at this point in time. So supervenience characterizes at least epistemic emergence. Now here's Dan Dennett, who I had mentioned before. He wrote a paper called Real Patterns, and in Real Patterns, he was specifically, a lot of Dennett's concern had to do with if folk psychological descriptions like hopes, desires, beliefs, that kind of thing, aren't how the brain works, aren't how cognition works at a more granular level, then why are they so effective, right? Because some of the early philosophical debates about the mind had to do with the effectiveness of this kind of folk psychological perspective to predict behaviors and this kind of thing. It's got to be the case that the brain works on these sort of large scale patterns like beliefs and desires and this kind of stuff. And Dennett wants to say, well, no, that's not necessarily the sort of functional description of what's happening at a more granular level. However, he doesn't want to dismiss the idea or disagree with the idea that folk psychological explanations can be um, predictive. So he says, well, what are we picking up there in folk psychological explanations? We're picking up these real patterns. And what are these real patterns for Dennett? They're informational. So he wrote this paper about real patterns, and where he basically says that a pattern is some set of information, and he uses images in his examples that remain self-identical despite modifications to the members of the set. And one of the examples you can use is something like JPEG compression, which I'm sure we're all familiar with. You can take a raw image on a DSLR camera, and it basically records pixel data for every pixel, what the color is um, in RGB for every single pixel. That takes up a lot of data to store that. So we come out with compression algorithms like JPEG compression, which instead of storing every pixel, it stores some group of pixels specified by a geometry and then assigns that group a particular value. So you can imagine how much savings that gets. Now, on the macroscopic level, we're still seeing quote unquote the same image, but in JPEG compression, a lot of that information has been lost on the pixel level. So the image that we're seeing in the compression, in terms of the geometry that the compression specifies, are real patterns according to Dennett. And I want to say that supervenience characterizes real patterns. As we remember, the supervenience relation is that no P change can happen without a Q change, but not necessarily vice versa. So there can be Q changes without a P change. Or another way to put that is that P is compatible with a set of Q states. P states are compatible with a set of Q states. So in terms of Dennett's real patterns idea, P can be compatible with a loss of information in Q, or some sort of average information over Q. So the informational relation, I want to say, is the supervenience relation on worlds from the multiple worlds interpretation of quantum mechanics. So, what is the upshot of this? We already spoke a little bit about what emergence is. So, the upshot is that as we live it in an emergent macroscopic world, we may very well be living across or over subatomic worlds. That is, our emergent world may literally be the sum total of a set of subatomic worlds and not just one such world as many worlds often assumes. Okay, so how to make that a little bit clearer? Um, in the standard interpretation of many worlds, although some people hedge on this a little bit, um, every possible subatomic difference, observed or not, can split the worlds or diverge, if you want to use the overlapping metaphor. The worlds can diverge from one another. This means that every time there is a subatomic event, say an electron happens to be here rather than there as it's going around its atom, uh, an entirely new world with an entirely new you gets split off or diverged from the trunk of the worlds. This is possible, but it seems to me like it may be more fruitful to consider that that macroscopic world of you um, literally exists over top of some number of microscopic possibilities. And why is that attractive? In part, and this is something that I'm going to talk about a bit later in another one of these barely adequate videos, um, in part, it helps to solve the hard problem of consciousness, or one particular potential problem in the hard problem of consciousness. In panpsychism, the view that the universe in all of its constituents has some semblance of like proto consciousness. There's something called the combination problem, where how do you get this unified consciousness out of a whole bunch of little bits of barely conscious stuff? If it's the case that our macroscopic conscious world literally exists atop a multitude of microscopic subatomic worlds, the combination problem dissolves a little bit. And that's because we don't actually have little point particles of energy, but rather smears of energy. And what we're actually conscious of are these literal smears. Um, there's a lot of detail, though, to go into that and a lot of provisos. So I'm going to leave that for another time. But in the meantime, this was my barely adequate expression of many worlds and emergence.